Good evening, everyone. First, thanks to the International Association for Fire Safety Science and all organizers for granting me this Best Thesis Award. It is indeed an honor for me to be part of this precious moment, to receive the award and to share my PhD works with you. Large-eddy simulation for purely buoyant diffusion flames. I made my PhD thesis from 2017 to 2020 under the supervision of Dr. Jean-Louis Gonsalvi and Dr. Fatia Nimira. This thesis was a fruit of academic industrial collaboration between Aix-Marseille University and Électricité de France, the French nuclear energy operator, so thanks to them for funding this PhD thesis. In today's presentation, I will first briefly explain the industrial and scientific context and therefore the objective of my PhD works. Then I will make the introduction to the physics modeling of relevant phenomena. After I will talk about the results and discussions for applications. Finally, its conclusions and perspectives. The fire hazards are one of the most important safety risks in nuclear power plants. One major reason is electrical sources that represent about 53% in fire hazards, such as electrical cabinet and cable trays, for example. They can pose risks like cause of fire outbreaks or favor the propagation of fires. A fire event can generate temperature rise, production of hot gases and toxic matters. It can also create an explosive atmosphere. For EDF as a nuclear power plant operator, its interests rely on the protection of safety of personnel and reactor facilities. It should comply with the regulation rules of French Nuclear Safety Authority. So EDF aims at reducing the fire risk by ensuring a high level of safety without using oversized firefighting means. Fire numerical simulation can be a very good tool because can identify the conditions conducive to fire and determine the induced effects and associated consequences through numerical studies. It can also analyze the adequacy of prevention, detection, and mitigations measures implemented, especially it's less costly compared to the experimental studies. However, there are many challenges in the fire numerical simulations. Take the example of canonical fire scenario, pool fire. This is a video of Hampton fire plume shot by our experimental colleagues on the IGNIS platform in EDF. The flows we see in the video are typically driven by buoyant forces with variable density. This can flow as complex patterns, first in the base of fire, and a continuous flame flare erection zone. Non-dissipating laminar vortices structures are formed because of relative instability and Helmholtz instability. And then these small structures are stretched in an intermittent flame zone and shut down the base, forming large-scale flow structures and subsequently a periodical puffing behavior. At last, the flow transits into full turbulent region in the plume area. The combustion of fire is usually characterized by diffusion flames. They can be well ventilated or underventilated. And there are additionally other physics processes like radiation and soot production. Taking the industrial and scientific context into consideration, the objective of my PhD work consists in development of a reliable LES-based fire simulator in closed turn for non-shooting purely buoyant well or underventilated fire plumes to handle turbulent flows controlled by unsteady buoyant forces. An accurate description of the turbulence and unsteady behavior is necessary. To this end, the LES and an adequate second-order accuracy Navier-Stokes equation solver are needed. The combustion and radiative heat transfer modeling in the AIS framework both need state-of-the-art models that describe properly the SGS level of behavior. The solver is ultimately validated through academic fire plume cases. Then I focus on the modeling issues. In the Large-eddy simulation, we solve the filtered Navier-Stokes equations. The mesh is regarded as a filter in such a way that only flow structures larger than the grade are explicitly resolved by LES, and that small-scale flow structures, namely subgrade scale, only exercise statistical efforts on large scales. Consequently, the SGS stress tensor and SGS scalar flux in the filtered Navier-Stokes equations required closures. We return the buoyant approach, that is, dynamic smart Gransky model for SGS stress tensor, and likewise dynamic eddy diffusivity model for SGS scalar flux. For combustion modeling of diffusion flames, the thesis returned the flamelet approach. In the approach, the turbulent flame is viewed as a collection of locally one-dimensional laminar structures, which is a flamelet. The flamelet depends only on the time and the normal direction to the flame front. It can be represented by a counterflow configuration, where we solve a set of laminar flamelet equations. As a result, the local flame structure is characterized by mass mixture fraction between fuel and oxidizer. The hypothesis behind this approach is that we have a high molecular number. That means the molecular level chemistry reacts much faster than mechanical flow timescale. A quasi-steady state is reached where the turbulent eddies only stretch and deform the flames, but the flame adjusts immediately to the flows. In the counterflow configuration, the chemical non-equilibrium is controlled by strain rates, and all thermochemical properties solved from laminar flamelet equations can be mapped from physical space to Z space. If we get all solutions to the flamelet system, stable, unstable, and mixing, we can have a S-shaped curve. We can find the stoichiometric temperature as a function of scalar dissipation rate. The steady laminar flamelet model only contains a stable flamelets tabulated into lookup library, where the flamelet progress variable model extends the lookup library by including the unstable solutions. This is essential to be able to simulate the flame extension process. In this model, we must have a proper definition of progress variable, and U requires a transport equation. For fire plumes, it's important to include the radiative loss impact on flamelets. We use the Carbonell's method. This method consists in tuning the radiative source term magnitude in the flamelet enthalpy equation. Following this approach, we can tabulate non-adiabatic flamelets into the lookup library with the parameter enthalpy defect. This parameter is defined as the difference between non-adiabatic and adiabatic enthalpies. As combustion occurs at unresolved scales, the SGS fluctuation exercises significant impact on the combustion variables. We use the presumed filtered density function to head the filtered combustion variables. And the presumed PDF, the beta function, is used for the mixed fraction. The direct function is used for other two parameters, scalar dissipation rates and enthalpy defect. For FPV model, the scalar dissipation rate is replaced by the progress variable. Then we get the filtered flamelet lookup table that contains one extra parameter, the SGS scalar variance, which characterizes the unmixedness at the SGS scale, and the filtered dissipation rate characterizes the rate at which the scalar reacts towards a fully mixed state. These two variables are, however, not readily available in the LES simulations, so they require closures. Here we use the Kyle and Raman's approach, where the filtered second-order moment of the mixture is transported. By definition, we will have the SGS scalar variance. Other alternative closure approaches were accessed too, such as direct transport SGS scalar variance and equilibrium approach. Details can be found in this paper, and we have seen the filtered second moment transport approach give better results than the other. As for radiation modeling, the filtered radiative transport equation is solved with the turbulence radiation interaction considered, the tree. The tree is composed by contributions from resolved scales and the SGS scale. The contribution of SGS scale requires modeling. The SGS absorption part is negligible when 80% turbulent fluctuations are solved. And for SGS emission part, the filtered PDF approach is used. And using the same presumed PDF mentioned above, the filtered absorption coefficient and the emission part are both tabulated into the flamelet lookup library. And they demonstrated that neglecting the SGS tree affects significantly the fire plume structures and the radiative flux predictions. The spectral dependency of radiation species property is modeled by the RCFSK, and finally, the equations are solved using DOM or FVM method. So far, we have seen the major modeling issues. Let's make a summary. We have seen LES modeling, combustion modeling, and radiation modeling. Lastly, the numerical solver used for the fire simulation in the Thesis is developed by coupling the scalar, density, velocity, and pressure based on the prediction correction algorithm. The second audio accuracy in time and space is verified and confirmed through MMS test cases. With these models in hand, we conducted the McAfee methane fire plumes to assess the SGS turbulence and combustion closures. It is worth emphasizing the importance using fine grids to capture buoyancy generated vortices structures, as we see in the video. And these vortices are in fact generated by the buoyancy and due to laminar instability that cannot well be handled by SGS models in LES. The most straightforward way to capture these vortices is to refine sufficiently the zone close to the burner. On the other hand, the simulation produced the scaling laws of velocity, mean temperature, and RMS temperature for fire plumes at different heat release rates. Now let's move on to fire dynamics with two applications, methanol fire plume and UMD methane fire. Methanol fire that has been experimentally studied by Wickman, Strong, Hamins, and other co-workers. This fire has a heat release rate of 22 kilowatts. The diameter of the burner is about 30 centimeters with a lip of 1 meter. In the later discussions, we will see the presenting this lip in numerical simulations of great importance. Here we show the results we see in the numerical data plots plotted for different locations for the fire. The left column shows the radial mean temperature and the RMS value of temperature at the two different heights above the fuel pan. And in the center, we have seen the different gas compositions distributions along the fire center axis. And the right bottom corner is the radial feedback heat flux as well as the total heat flux towards the fuel pan. All numerical profiles fit quite well with the experimental data. And then we can look at the unsteady puffing behavior. This video recorded the vortice diesel contours after first Fourier transform. We get the puffing frequency and compares very well with the experiment's data. The result indicates the fire simulator can reproduce faithfully the complex unsteady behavior of fire plumes. During Thesis, we found that the burner's geometry has great influence on the fire dynamics. Here we conducted the simulations on 3 different types of geometry. The first case, the baseline case, is identical to experiment with a lip of 1 centimeter and the burner lifted by 30 centimeters above the floor. And the second case, no lip case, in which the lip is dropped. In the last case, there's no lip and the burner is directly located on the floor. These results are presented in the videos, and from the videos we can see for the baseline, we see the flame is anchored on the top of the lip, and the flame sheets are raincoated by the entrant air, and the hot bubble structures are created and become huge coherent structures through the radiator instability. Enhanced air entrainment mixing observed too. In the second case, the flame is anchored to the burner's edge, no flame wrinkling, and non-hot bubble structures are noticed. And the coherent vortices are smaller, consequently, there is less air entrainment capability. In the last case, only horizontal air entrainment is possible due to the floor remark narrower fire plume with fewer vortices, and therefore further reduction in the air entrainment with a noticeably faster puffing frequency. And the reason for the difference in the 3 behaviors relies on the vortices source term. It's decreasing from the baseline case to the no lip end case. The vortices source terms depends on the magnitude of density gradient as well as angle between the density gradient vector and the gravitic vector, namely the baroclinity. I will show the oxygen diluted fire plumes experimentally studied by White and co-workers at the University of Maryland. This fire is a 50 kilowatts methane fire on a line burner with a lip. Fire extension is controlled by nitrogen diluted air from normal air case to oxygen extension limits. There are two configurations considered, no oxygen anchored and oxygen anchored case to establish flames. Both LCLF and FPV flamelets models are assessed in numerical simulations. For the oxygen diluted flamelet manifold, 6 oxygen mole fractions are considered in the flamelet generation, from 21% to 13%. If we plot all S-shaped curves as a function of decreasing oxygen fraction, the extension point is shifted towards low strain rates. As we have said, in the FPV model, we must define the progress variable. The adopted progress variable is the sum of mass fraction of CO2 and H2O. In fact, more detailed discussions and definitions of progress variable can be found in this paper. Finally, we chose this simple definition because it provides generally good flamelets mapping on the unstable branch throughout the well-ventilated case and under-ventilated case. For the results of a well-ventilated case, the left two figures show the mean temperature and RMS of temperature along the fire center axis predicted by the SFF and the FPV models. Then in the right panel, we have the radial profiles at different heights above the burner. The numerical results generally fit with the experiment data, except the RMS values are both overestimated by the two models in the intermittent flame zone. We can conclude that SAF and FPV both obtain good fire structure predictions for well-ventilated fire plumes, and their results are similar. And then let's look at the effects of oxygen dilution. Because of decreasing oxygen supply, we evidence the reduction in flame luminosity in the experience. And the flame turns blue progressively. In the non-anchored case, the flames detach from the burner at oxygen fraction 15% and then extinguished. In the oxygen anchored case, we see the flame extension occurs until 13%. It also plots the radiant fraction, convective fraction, and combustion efficiency results in the right side figure. From this comparison, SLF only predicts the fire if no extinctions happened, and for non-anchored case, PV predicts the flame detachment about burner and the subsequent liftoff. For anchored case, FPV also predicts the gradual decrease in flame luminosity and the progress increase of local extinction throughout the whole flame body. FPV well predicts the radiant fraction, convective fraction, and the combustion efficiency both for anchored and non-anchored fire plumes. For conclusions, the state-of-art models dedicated to non-sorting fire plumes developed and implemented in the Saturn, which is accessible by open source. And this simulator is verified and validated through the academic case. It well produced fire structures of fire plumes in both well or under ventilated conditions. And thanks to the FPV model, the simulator captures the local extinction of flame liftoff in oxygen diluted fire plumes. Especially, it should be mentioned that close to the burner, mixing is controlled by the laminar instabilities, and sufficiently refined grade and correct burner geometry presentation in the numerical simulations are very important. And perspectives as instability-induced mixing is always an important and fundamental problem in the modeling of fire plume dynamics. Because significant mixing due to laminar instabilities close to the burner can't be handled by current SGS models. Although attempts have been taken to model this effect, no conclusive model so far. We need also advanced tabulation methods that are required for constructing a lookup database in the future developments. Nowadays, we use a 4D lookup database and to store the thermochemical states. With new applications in the future, database dimension still increases, and the classic method of interpolation will not be realistic. Thank you for listening, and a special thanks go to Jean-Louis Gonsalvi and Fatia Nimura, who supervised my PhD thesis. Without them, I cannot succeed in my thesis and cannot be here today. Thanks also to Jean-Marc, Martin, Yvon, and everyone for their technical support during my thesis. I thank Christelle too, who was my team manager when I was a PhD student. And I will never forget all the PhD colleagues who shared time with me, like Sarah, Lucy, and Hamza. Thank you all.